So like, I think the first one. So usually with these, eventually they will.
Yeah.
So if you're not convinced, just keep going.
Thanks, Michael.
Oh yeah, I just. Yeah, it does, and then I was like, wait,
All right. If you are not finished, I'd like you to put that off to the side. We're going to do some comparison tests now. You are probably going to like these quite a bit because they will allow us to use P-series and geometric a little bit more, which are two relatively easy tests. So I'm going to pass out these notes. We're going to do a little bit of talking at the board. And then there's literally only 5 questions on the board. And they don't take very long. Theoretically, more calculus time. I would love that. More All right, so comparison tests. I want to start talking before we hit your notes about a little bit of intuition on these tests. So I have a bunch of series up here. They're not on your notes, so if you could just kind of pay attention at the board for a second. These comparison tests, I would argue you're gonna know the answer pretty much before you start your question. So looking at this series right here, does this series kind of look like something that we've already done? What does it kind of look like? Maybe a telescoping. I think it looks a little more similar to something else. All right, looks a little similar to integral test. I don't know how to integrate this. I think it looks really close to a P series. Let's say I said this is all, whoa, that's a thick pin. I did. I also had it a little bit thicker than I normally do. This is almost the same as this series, right? 1 over n cubed. Do you think as I approach infinity that plus 1 on the bottom is going to do very much to this series? Probably not going to do all that much. So what we're going to learn how to do today is write a very formal way to compare these two series. Now let's check our knowledge. If this is a P series, what do I usually look at? The power. What is this power? Why do I care? So what does this series do? Which one? All right, if you think about the integral test, if you pull that up as n to the negative 3 and add 1, you're still getting n to the negative 2 still on the bottom there. Let me check. Yeah. Yeah. Mm-hmm. That's great, but it doesn't work for everything. A good example would be the harmonic series. That one, the numbers will get bigger and bigger on the bottom, so smaller and smaller fractions, but that guy diverges. So works some of the time. Unfortunately, most of our series, they will get smaller and smaller as we go. All right, let's look at this one. What does this guy look kind of like? I know. Was it? Oh, we're going to do that one in a second, formally. What does this one look kind of like? Hold on. Okay, just look at the board. Don't look at your notes yet. I did announce that, but no one was listening. So, cool. All right, looking at this one. So notice, this one looks kind of like a P series. What does this one look kind of like? All right, doesn't it look kind of like 1 over n? All right, that one's harmonic. What does the harmonic series do? All right, you don't need to write this down. Just look at the board. All right. What does this one kind of look like? That's a little creepier. Well, what have we been doing so far? What have I been kind of doing? Comparing, yes. All right, this one kind of looks like a geometric. What geometric do you see, Caitlin? All right, I see 1/2 to the n. How could I rate that to make it look even more geometric? Yeah, I could make this 1/2 to the n. So this looks super geometric. How do we do geometric again? Okay, so absolute value of r is 1/2. Why do I care? So what does that do? Converges. We're just intuition right now. All right, thinking of this, what does this one look kind of like? Nth term? Oh, we could use nth term on this one. What if we had to compare it to something? What could we kind of compare it to? This, yeah, 4 to the n over 3 to the n. Kind of looks like that one. Yeah, I heard that over there. So I could do like 4/3. It's geometric. Yeah. What would r be here? Ooh. 4/3. I can't write. Why do I care about 4/3? So this does what? All right. Do I have one more? Ooh, interesting. Ponder with your neighbors. So look at what I've been doing, what I've been keeping, what I've been leaving off, and all of these. Think about that. And think about what might I compare this one to? How could I find something that looks kind of similar to this? Think about what you would keep, what you would get rid of. I know this is a little weird. We're starting off with something that's not on our notes. We're just thinking about it. What could I compare this to? Anyone have an idea? Zach, what's your idea? All right, I'd have to do like some partial fractions if I want a telescope. So let's get away from the idea of telescoping. What? Any other thoughts? What do you mean take out an n?
I don't know, like factor out.
Oh, we could factor out an n in the bottom. That certainly would make our series look simpler. So if I divide everything by n, I could have like, yeah, I could have an n on the top, a 6n to the 4th minus 5 on the bottom. That makes it look a little simpler. How could I compare it to something even simpler? What have I been doing on all of these? Have I been keeping the +1, the -6, the +1, the -n? All right. Couldn't I kind of disregard this -5? Maybe even disregard this 6 here and be like, okay, this looks kind of like if I had n over n to the 4th. Can I simplify that? 1 over n to the 3rd. Is that now a series that I know what to do with? Yeah, what kind of series is this? It's a P series. So I can't actually, we're trying to figure out how we can make this look like something we know. We're going to find the formal way to compare. But right now, I just kind of want to show you how we might break these down into something we can compare to. So here the P equals 3. That's greater than 1. So we converge. So what I want you to get from this little intuition discussion is I'm going to be looking at the thing that's growing the fastest on top and on bottom. If there's only stuff on the bottom, disregard a +1, disregard a -6, disregard a +1, disregard even a -n if you've got exponentials in top and bottom. Or if we're getting more complicated, let's just take the winning power on top, the winning power on bottom, and see if it simplifies into something I know what it does. We're going to have to choose what to compare to, and that's kind of how we're going to do it. Let's now talk about a formal way to compare. So we're going to get 2 formal ways to compare. What I want you to also notice is that once we decide what we're comparing to, we're kind of going to know the answer to the question right away. As soon as I pick, oh, hey, I want to compare to this geometric, you kind of know what the answer to your question is going to be. So the real tough part in this is we're going to have a formal way to say what I'm comparing to. I know this does exactly what I think it does. So let's start with direct comparison test. I'm going to be honest, this is my least favorite of the 2 comparison tests, which is why we're getting it out of the way first. If it works, it's much easier than limit comparison, but that's a pretty strong if. So we're going to have, this is now on your notes. So if you have your notes, now would be the time to get out your pencil and get ready. So we have two different series. We are guaranteed that both of our nth terms are positive. So this is good when I have positive terms only. That's because I'm going to be comparing those two nth terms. So let's say our series, we know that one of them converges. We can find a comparison. We know it converges. This is the one we know converges. And the one we're comparing it to, the one that we don't know about, has terms that are only smaller than that. So I'm adding up infinitely many terms of b sub n, I get a number. If I'm adding up smaller terms, would you also agree that I'm going to get a number? So if I add up smaller things than something I know converges, then this one has to converge as well. Now, that's a little hard to see in notation, so I'm going to write the words that I say to myself, and that is smaller than a convergent series converges. So we know if I add up infinitely many terms and I get a number, I get a sum, that's what converging is. If I add up smaller numbers, I should get a smaller sum, but that will definitely still converge. All right. If I have a sum that diverges, so all of the numbers add up and they are too big to have a sum, we get infinity for our sum, it's too big, and I add up stuff that's bigger, that's also going to add up to something that's too big to be a sum, so this one will diverge. So that is bigger than a divergent diverges. All right, now all of that's pretty still notation heavy, a little theoretical. So let me show you with 3 questions how we set this up and how we kind of provide a rigorous proof for each one of these. For the comparison test, the one annoying thing pretty much every year that people just get really perturbed by is the comparison tests are going to feel like you're doing 2 tests at once, because you have to say what the thing you're comparing it to does and then use your comparison test to say something about the question we're answering about. So let's start with this one. This was the first one we did on our little intuition thing. I'm going to start by writing off to the side what I will be comparing this to. So I always say compare to, and I'm going to keep my series notation. We want to make sure we're comparing a series to a different series. All right, what thing do you think we're going to compare this to? A p series. We're probably going to look at 1 over n cubed. I'm going to write the exact series I'm comparing this to, and just like Michael said, I'm going to call this a p series. We're going to do the full p series test on this thing over here. So I'm going to identify what p is. Do you guys agree that it's 3? All right. Why do I care about the number 3? It's greater than 1. So what does this p series do? Converges. So if we're hoping to make a conclusion on this, I'm hoping that the series I want to know about with the nth term 1 over n cubed plus 1 is smaller than the one that already converges. So what I'm hoping is that this nth term is smaller than this nth term. All right, remember that we only have to have that be true on the domain. So for n is greater than or equal to 1, is that inequality statement true? Are you convinced? All right, a bunch of people are nodding their head yes. I would be convinced from here because I'm making the denominator on the left-hand side 1 bigger than the denominator on the right-hand side. If you're not convinced, you can certainly do some algebra. So you could cross multiply here, get n cubed on this side if I multiply by the n cubed. So this stuff in green is kind of optional, is less than n cubed plus 1. You could even subtract n cubes and get 0 is less than 1. That's kind of like a very rigorous formal check. But I would say looking at this inequality right here, I'm pretty convinced this fraction is smaller than this fraction as long as my denominators are positive. if we can show that the terms that we're asked about, the 1 over n cubed plus 1, are smaller than something I know converges, we can say that this original series converges by direct comparison test. A lot of you guys have been asking about acronyms because you don't like asking. DCT is fine, both on my test and the AP test. Now, the problem with direct comparison tests is if that inequality is not true, I can't use direct comparison tests. So for example, if that had been n cubed minus 1 and that fraction was bigger than the fraction we're comparing to, I can't draw a conclusion. So normally with direct comparison, it's going to be a very simple change from the series we're comparing it to, and it has to be in the right direction. Let's try a couple more. Then we're going to have to use a different test. Don't worry, it's the one on the back of this paper. All right, so in the next 30 seconds, I want you guys to come up with at the very least, what we're comparing it to. If you're feeling pretty comfortable, go through the series test on what you're comparing it to. So at the very least, think of what you want to compare it to. If you can, try to go through the series test of what that is. Does anyone have an idea? You do? Does anyone want to share their idea? You think it's geometric? So what geometric one do you think it is? 1 over 3 to the n, which some of you, I think I heard some people mentioning would be the same thing as 1/3 to the n if I want to make it look a little more geometric. Do you guys agree with Brandon that this would be a geometric series? All right, how do we show a geometric series converges or diverges? All right, so we're looking at absolute value of r. This time it's 1/3. Why do I care? All right, so what does this geometric series do? Yeah, P series and geometric, I wish I could change the fact that it's like exactly the opposite. Geometric, you can always think of, I want to make the terms get smaller. So if I'm multiplying by a fraction, that's usually helpful, like a fraction like 1/3 that's less than 1. For P series, you want to think back to that integral. If I add 1 to the power, will it still stay in the denominator to converge? All right, so let's think about the inequality that we need to set up. So I want this one to be compared to the one we're comparing it to. What inequality am I hoping to write down? How do I want the one that I'm being asked about to relate to the one I know converges? Do you guys agree with Brandon that we want it to be less than? All right, if we have that one converges, if I add up smaller numbers, it should also converge. So is this true? Mason looks convinced. Is everyone else convinced? If I add 2 more to this denominator, that's going to make the denominator bigger on the left than it is on the right. That less than is preserved. Again, if you wanted to be a little bit more rigorous about it, this is not necessary work, but you could kind of cross multiply, subtract out your 3 to the n's, and get a very clear comparison of 0 is less than 2. Yeah. Yeah, in this case, it's actually true for all n, but you could add on that for n is greater than or equal to 1 to add to that kind of series domain. But this one is true because it's exponential. Awesome. Do partial fractions on this? I don't think I've ever tried partial fractions with an exponential. I actually don't know how that would work because partial fractions, as we did it, was for linear factors on the bottom. You can extend that into quadratic and cubic, but I don't know how it would work with exponential. All right, so am I done with this question? No, what's my answer? Perfect. All right, let's try one more and then maybe a break. Yeah. I like these tests though. These are pretty, not too bad. No, it's just giving a very formal way to compare the two. And you guys are going to like limit comparisons, so don't worry. All right. Anyone think they know what I'm not going to say convert, compare to? All right. What do you think we'll compare this to? 1 over square root n. I like that. How could we rewrite that to make it look more familiar? All right, n to the 1/2. Why? I heard to the power of 1/2. So what type of series is this? It's a p series. All right, what is p in this case? 1/2. Why do I care? Less than 1. All right, get your comparisons to 1 straight in your head. Does that mean this p series converges or diverges? I like to think of the integral test for this. So if I integrated this term, the ends would go up to the top of that fraction. So negative 1/2 is the power. Adding 1 would make it positive 1/2. Yeah. So when I go and write for n is greater than or equal to 1, I'm actually going to do n is greater than or equal to 2. The reason this one's starting at 2, think that if you plugged in 1, that first term would be undefined. So that's why they might shift the beginning. Okay. All right, so let's go back to this. So we've compared, we have exactly what our comparison series does. I'm going to set up the one I want to know about with the one I do know about. All right, to make a conclusion, we have the one on the right definitely diverges. So what inequality statement do I want to have in the middle to make a conclusion? Do I want this one to be greater than? Yes, absolutely. So I want this one to be greater because if that adds up to infinity to make a conclusion, I need to know that that one's actually bigger. Is that true? Yes, I'm making the denominator on the left smaller, aka the fraction's getting bigger. If you want a more thorough comparison, not necessary, but you can get a more thorough one by cross multiplying and kind of getting that final thing. So our final answer diverges. That would probably be nice. So I switched the order there. So this is smaller one diverges here. This one's bigger. So I usually just think about the inequality that I would want to have makes a little bit, because I'm more working off of the words. So the one I want it to be bigger than one that I know diverges. Yeah, Caitlin. So if it was equal to it, we would probably just simplify and use a p-series test. So usually these are going to be a slight difference off of the ones that we already know. All right, we're going to take a break right now, but I want to kind of tell you where we're going next. So if you weren't the biggest fan of this test, then join the team. I find this test to be a little wishy-washy, and though it has not a lot of work, it doesn't work all of the time. So we're going to do another comparison test for ones that look a little bit more complicated. So notice these are a little bit more complicated. I wouldn't be super confident saying the first one is exactly greater than or less than a simplified version. But we're going to be able to use a limit and it will work every single time that we do a comparison test. So let's take a solid break. I'll even go 5 because you all look sad today. All right. And we only have 2 more problems to do. Only 2 more, Mr. Prince. Thank you. Not that long.
Oh, she just made it brighter for a second.
I didn't want to make it all the way dark.
No, there's a light switch that offers you 2 lights of the 3, or there's a light switch that offers 1 light of the 3. I prefer 1. My team teacher prefers 2, so I always end up switching. That's just bright.
Oh.
What? Everyone's real grumpy today. Same.
I don't know about me.
For me? Thank you. For me? Thank you.
It looks like it. Yeah, the funny thing about P-Series is we didn't even need to do any of that.
Oh.
Yeah, that was like the max if we wanted to. P-Series is this. Then we would just take the left. Then we would use that's where you go. 703 is greater than 212. So this erase that. So we just need this. 703. Right there. And it's 702, but make sure you have it the same. And divide it. Or not divide it. And then yes,
All right. So we got 2 more questions to do. I promise this test is probably going to be one of your favorites. While we do this test, I want you to start thinking about the upcoming assessments we have. There's going to be some rules for some of them and not for others. So just to warn you, on the quiz that's coming up, I'm going to force you to use each test that we've done once. So there's going to be one where you have to use direct comparison, one where you have to use limit comparison, one where you have to use this, have to use that. You're going to be in charge of choosing which ones to use, but I'm going to make you use each test once. Now, that's a little mean because at the end of the day, you're not going to have to be able to do each test once when we get to the final assessment. So kind of on the quiz, I'm going to make sure you can use all of them. But when we get to the unit test, if you're just like direct comparison, I hate you, goodbye, that's fine for the unit test. So on the quiz, there'll be one. But to be quite honest, I usually use limit comparison instead of direct comparison just because I find it easier and a little more formal. So what we're going to do is we're going to take a limit as n approaches infinity of the ratio of the two series we're comparing. So I'm going to divide them. And we want to get a number that is both finite and positive. What that finite and positive thing means is essentially that our test works. So let's talk about these two words. What does finite mean to you? It's a number. So essentially this means I don't get infinity. Positive, we're not really going to get a negative number here because we're guaranteeing that all of our terms are greater than 0. So what positive really means in this situation is we're not going to get 0. So if we get a number that is finite and positive, that means our test worked. So that means that whatever we are comparing to, our series does the same thing. So if our original one converged, the one we have converged. If the one we're comparing to diverged, the one we're looking at diverges. So let's run through this a couple of times. You can probably imagine why we're doing this 2 times. Let's talk about what we're going to compare to. So all of our comparisons are going to start with choosing what to compare to. Thoughts on how to choose what to compare to here? You have a guess? What's your guess? Okay. Anyone want to make that smaller? I'm actually just going to pull highest powers from top and bottom. So remember back when we did limits and we were just like, you know what? The one that runs the top is n to the 4th. The one that runs the bottom is n to the 5th. We're going to literally disregard everything else. So we're going to talk about n to the 4th over n to the 5th, which you can imagine I am about to simplify. Now, notation-wise, notice that I'm keeping this series notation the entire time. I want to compare a series to a series. Oftentimes, my students will get a little lazy and do this. That makes me super mad because an nth term is not equal to a series, so make sure you're keeping that series notation. What will this simplify to? N to the 4th over n to the 5th. 1 over n. Oh, he looks familiar. Who is that? Harmonic, you could also call him a p series with p equals 1. What does the harmonic series do? Diverges. All right. So we're going to set up a limit here. Now, I am going to set up the first step, and after this time that I do it, I'm never going to set up this step like this again because it looks really dumb. I'm going to set up the limit as n approaches infinity of the thing that I have. So n to the 4th plus 5 over 3n to the 5th minus n squared plus 9 divided by the thing I'm comparing it to. Now, that looks, to me, horrific. I don't like the way it looks. What would you rather do than divide by 1 over n? Multiply by n over 1. So normally, I will start here. That being said, we could also flip the order of this division. It actually doesn't matter because we're just looking for a number that's finite and positive. So normally what I'll do is the one that I want to know about times the one that I do know about. All right. Let's go ahead and I'm going to take that n on the top and distribute it into the stuff on the top of my limit. So that is now n to the 5th plus 5n over 3n to the 5th minus n squared plus 9. All right, over the course of your calculus career, you've probably evaluated about 1 million limits that look like this one without writing down any work. Anyone think they know what the answer to the limit of this is? 1/3. We got same power top and bottom. So we're doing ratio of coefficients. So we get 1/3. Now, be careful. We got the number 1/3. Why do we care about it? There are two words that we want to know. Is it finite? Yes. We got a number, not infinity. Is it positive? Yes. So what does that mean? Good. A lot of people are going to want to sit here and say converge, because usually when things work, it converges. All that means is that the test worked. Our comparison test worked. So it does the same thing as whatever our comparison test did. So this guy diverges by limit comparison test. Yes, you wished it into existence. You can call that LCT.
So if it is a finite and positive, is it?
That's a great question. So if you get infinity or you get 0, essentially that just means user error. So you chose the wrong thing to compare it to. So if everything's working correctly and you chose the right comparison, you should get something that's finite and positive. Essentially, you want to choose something that has kind of the same strength as your series. So if you get something that's infinity, you chose something that is not strong enough. If you got something that's 0, you chose something that's too strong. Yeah, Mia.
So, positive is not 0.
Yeah.
Not 0 or negative.
So because actually one of the stipulations of using this test is that our terms have to be greater than 0 anyway, because this wouldn't work for an alternating series. We're going to have a whole different test for that. That's super easy. So because the terms have to be positive, the only way to not be positive would be 0. Yeah. All right, let's just try this one more time to make sure we've got it cemented in our head. So tell me. Actually, this is a good example. This one kind of looks like direct comparison, right?
Yeah.
All right. Let's talk about why that wouldn't work. What would you compare it to? Either way.
1 over.
All right. Do you guys like Brandon's 1 over n cubed? Love it. We're essentially just going to choose the top power, top and bottom, see if we can simplify it here. We're not going to have to. What kind of series is 1 over n cubed?
Geometric series.
P series. What's the difference? Does anyone know the difference between? Yeah, so the n's the base here, the number's the power. For geometric, usually the number's the base, the n is the power. Have you noticed that everything we've compared to today has been a geometric or a P series?
Yeah.
All right, that is a theme, that is a pattern that you can stick in your brain. Those series tests don't take very much time, so they're great to compare to. We could compare to something that we do with integral tests, but that would just be like a whole thing. Yeah.
The fact that the n, like the power and the base switch to y.
Maybe not in like as consistent a way as you would want, but kind of. All right, P here is 3, right? Why do I care? So this does what? Converges. Aren't you so glad we're talking about P series and geometric so much? See, now you're going to remember them. All right, so let's say I wanted to do direct comparison test here. It's not going to work, and let's see why. If we had the one that we want to know about and the one that we know converges, what inequality symbol would I want to see here? If I know something converges, what would I want to see here? I would want to see less than. Is that true? No, look, that denominator is smaller, so that fraction is bigger. So direct comparison is not going to work here. That being said, limit comparison, he always works.
So for a comparison test, limit test will always work in that way.
So on the quiz, what I would be looking for, and I was going to talk about this in a second, there's going to be an order in which you want to look for your tests, and I'm going to tell you mine before we leave today. So I've put the one that I want to know about. What should I multiply by instead of dividing? Yeah, n to the third over 1. So essentially the reciprocal of the one I do know about. Without well, I guess I'll simplify. Why not? We always love writing more. What is this limit equal to? All right, Lily claims 1. Do you like her 1? All right, same power top and bottom. Coefficients are both 1. All right, why do I care about the number 1? All right, it's finite. It's not infinity. It's positive. It's not 0. So what does that being finite and positive mean? All right, this means the test worked, which in this case does mean that our series converges because our original one converged. So converges by LCT. So again, if the test didn't work, you chose the wrong thing to compare to. So it's more like a user error thing than anything else. In that case, you would probably want to just go back to your comparison and make sure you grabbed the right series, or you did like your algebra right when you were simplifying. All right, so talking about all of this, we now have a lot of series tests, right? We had 5 that we reviewed at the beginning, and I added 2 more on today. I'll tell you on the quiz that P-series is not going to be one of the tests that's going to be on like the back page of all the convergence divergence. So I posted a quiz. P-series comes up the most either within a comparison test or in some multiple choice. So if you look at this quiz review, this first one, which of these series converge, those are all P-series ones. Here we've got a little geometric, we've got a little geometric, we got a little P-series here. Find the sum of the series. What are the only 2 types of series where we can find a sum? Geometric's the first one, telescoping's the second one. The majority of your work is going to be spent on this back page, and it's going to be formatted exactly the same way on the quiz. I actually pulled harder questions for this review than the ones I believe are on the quiz. So here's how I would do this part of the test. The first test I would look for, does anyone think they know? I would look for nth term first. That's because there's only going to be one of them that works. All right. If I look for nth term, anyone see it already?
Oh, is it one thing?
What do you? Yes. So I'm going to use each test once. All right. I heard someone say the first one. What's the limit of that nth term? 2. Why do I care? Not 0. Wow. Okay. Literally everything else in here goes to 0. So I would want to be a little concerned. So I would look for nth term first. Then I would look for series tests that I don't normally want to use. For me, those 2 series are direct comparison and integral test. So for direct comparison, I would look for something that looks like a series I know, but is a little bit different. Does anyone see one that might work for direct comparison? I think there's 2 that might work. All right, which one on the left? All right, middle left. That one looks kind of like a geometric, so I might see. Or this one might kind of looks like a P-series. So I'd be looking for one of those because personally for me, direct comparison, not my favorite. Integral test, also not my favorite. Any thoughts on which one might be integral test? All right, top right. This one looks like it needs U sub, right? So that is a good thing to use for integral test. And then from there, the geometric ones, you're looking for things to the nth power. Telescoping is kind of in your face. That bottom right one. Yeah, telescoping is nice. So you're going to want to think in the past, the best advice I think I've given is before you start working on the test, kind of just go through and identify which test you think is going to work with which one. So you're going to start to get a preference. And then once you get to the actual Unit 8 assessment, you can use whatever the heck you want. So yeah, let me show you. Oh, she has a box. She has a box of stuff for me. Seniors, get ready. We're going to start giveaways. It's almost 100 days to graduation. We're raffling something off every day. Yeah. Yeah, the first day it's going to be 100 of something. So it might be like a $20 gift card and like 80 stickers. And then the next day, it's going to be 99 or something. So it might be a $20 gift card and like 70 lollipops and 9 glow sticks.
Yeah, that's a pretty good offer.
Then I don't know. There's 100 days. You have a pretty good. You have like 1 in 3 shot of winning something.
Yeah.
Pretty good odds, man. We're gonna do random number generator. No, you have to be a graduating senior. We're gonna announce it. Probably on the morning announcements. We'll have it rolling on the thing at lunch, and I'll probably put a sign on my door.
Like 3 times.
No, it will be 1 winner. The last week of prizes is pretty thrilling, not gonna lie.
I hope I don't win.
There's a lot of gift cards. We got a lot of like small tchotchkes for the bigger days. So like 100 is obviously a lot of things. The stickers are pretty cool. We already got them. There's some glow sticks, some stress balls, little graduation rubber duckies, which are really cool. Hope you win then. The final week, I think there's a TV.
How big?
I don't know. Oh, like a mini fridge.
Oh, wait, I want the mini fridge more than anything else you just said.
So it's gonna be exciting. Spread the word. You'll at least most of the big ones. You at least get like a $10 to $20 gift card. All right. No. There's 300 people. We gotta get 100 winners. All right. So before we leave, we've got about 10 minutes left.
Oh.
You know what happened? In Unit 7, we didn't do any nose checks. And then some of you were like, I don't know what we're doing on the test. So we're going to make sure we do nose checks. So you have 2 convergence, divergence tests. I even was nice enough and told you whether to use limit or direct comparison here. I'm going to roll around with these. There are different versions. If you're feeling nervous about today, I would work with your neighbors and feel free to get up. And let's say I have version A and Brandon has version A. I could be like, yo, Brandon, let's check each other's actual numbers. That's fine. Cool. Great. I haven't been as strict with rules on nose checks. That's fine. So let's practice these. I'm also going to come around a second time with this quiz review. I will tell you this quiz review. Look, answer key already posted. Wow. All right. I would pay particular attention to notation. Again, I just want to keep emphasizing. Don't want to give away the answers. Don't want to spoil it.
Just showing them off.
Yeah. Keep in mind that this entire unit, if you can tell me converges or diverges, that's not really that cool. So the cool part, the part that's worth the points, is the argument, the notation. So make sure as you're practicing these questions, compare your notation to what I'm putting out there, because that's kind of the model, if that makes sense.
Okay.
All right, next class, we'll also have the first half of class will be just review. So bring your problem sets, all of your notes checks to correct. And we'll only take the second half of class to take that quiz, because it's going to be just as short as that review is right there.
Literally just going to be.
You will. It's not so hard. I promise. You just got to make sure you do your NP, which we practiced the geometric and P series today, so that'll be good. Now we got to fill in all these weird people that were absent today.
They're just gonna come back. Why am I getting?
Oh, is that the day they go to like Patrick Henry and do the?
I think that's today because we got
And
tomorrow.
A song.
What are we comparing it to? Gosh, right. Gosh, dang it. Gosh darn it. Same thing. What are we comparing? That's right.
unfortunately not on it, but.
It has to be just, and.
No, I think it was something.
So you prefer staff, ideally, you'll work on this.
Is this, somewhere over?
Yeah, and the quiz is gonna be exactly the same. It's just like a different quiz, I mean, slightly different format, exactly.
Bottom line.
All right, did I get reviews for
I want to
everyone?
check
Yes.
something else. Or I'm not saying I'm.
Oh, I forgot I have even more questions. Wow. If we had extra time.
Before comparing.
Yeah, that's so enough. Yeah, either way, whatever way you're gonna.
Yes.
Does 1 over n squared average?
What kind of series is it?
That would be easier. So if you have n plus powers, then it'll be that guy, bigger than powers. So if you look, this is the percentage on the C, how long the series is, the x is gonna end up staying in the denominator. If that happens, you're gonna, you're gonna have it like. Yeah, one of all the powers, that's what x You start off the one. And it should be less. Oh, okay. So.
For me? Thanks.
At least we can correct them.
What? Why do you need to correct it?
I don't know. That's just the kind of day I'm having.
Looks fine.
Oh, does it really?
Yeah, I mostly just wish there was one equal sign right here, but that's it. It's fine. It's like the littlest thing. Hello. Thank you, sir. All right, we still have about 5 minutes to the end of class. I'm going to do announcements when we have about 2 left. Hang on.
So you can say is that like if the series converges, whether it converges, it converges. And make sure if you're putting equals, the series notation. What? My ears weren't here anymore. Yeah. I would see what that is.
Oh, yeah.
If they both work, I should because. So. Yeah, so essentially this means that whatever door one that you're comparing to, like the other one does. Kind of like.
What is this one?
No, they don't.
I'm not feeling right.
And then do you want me to ask for limits? Do you want me to use?
Oh, I just don't Wait, I didn't know.
No,
Should I
she
put it-
says,
put it down?
Oh.
again, you can do it, and you're usually gonna try to do a reset. You should end up from the bottom. Theoretically, that. Hello.
I did that too.
Mine is read my direction. Right, well, at least you know. Direct is the easy one to do the back side, because then you just have to set up the you can use all of them. Just set the other. I don't have all my stuff in here. And I don't, every chapter.
Oh.
Probably, yeah. Yes. Oh, thank you. Oh, Mason's too, thank you, Mason. Yeah. 2 minutes.
Can I ask you to do something for me?
Yeah.
The only thing that hasn't clicked in my head yet, and I'm glad it's the only one because it's very easy from what I've been told, is N.
Yeah.
Can you briefly explain it to me?
So in my head, what I like to do, the end term test, you're taking the limit of the thing that's inside your series. If that thing doesn't go to 0, you know you
So what should I look for
So
when I'm
I
trying to
usually
find it?
look for, I usually try to take the limit in my head. So like here, if I take the limit as n approaches infinity, I got more stuff on the bottom and cubed on the bottom versus m squared on the top. That one's going to 0. That one looks like telescoping already.
Yeah.
This one, the 4 to the n is bigger, so that one's going to 0. Only n's on the bottom going to 0. Only n's on the bottom going to 0. This one though, same power top and bottom. So I take the ratio 2/1. That is not 0, so that's what I'm looking for.
And then you just
Mhm.
limit this.
So you just limit nth term. If it's not 0, not 0, divergent.
Got it. Okay.
Thank you.
Come here and gifts.
Oh, thank you. Probably. Yeah. Perfect. All right, before we leave, I need your attention because I got less than a minute. So ears open. If you're still working, keep working. Next class, we have our quiz. You have the quiz review. I promise. That looks extremely similar to the quiz. The directions on the back are going to be identical, just some little adjustments on the series themselves. I'm going to try to make them definitely easier though. For the first half of class, you're going to get time to correct the notes checks that you're turning in. Even if it's not done, I want you to turn in what you've got. Bring your problem set to work on next time, and you can work on that quiz review. Again, the answers to that are already posted. Send me questions, concerns, comments. Thank you guys for your hard work today. I'll take anything you still have notes checks wise.
I did limits for both.
All right, then I'll highlight one for you. All right. Happy Tuesday, everyone. Have a good day.
Water.